Okay, let's continue with FRQs for number 5 and number 6. So number 5, this is a problem that where we have a function that's defined as the definite integral of another function. So the graph of a function f consists of a semicircle and two line segments. So we have a semicircle, two line segments as shown, and g of x is equal to the definite integral from 1 to x of f of t dt. Okay, and so that's basically saying that f of t is the derivative of the g of x function. I'm just going to go ahead and get this out of the way. We're just going to go ahead and find g prime and g double prime, just so that we can see clearly, more clearly, the relationship between g of x and f of x. The definite integral of f of t is simply going to be g of x. So if I want to find any ordered pair for g of x, I can simply plug 1 or 2 or 3 into x, and I can just add up and find the definite integral using areas of semicircles and triangles. But if I want to find g prime and g double prime, I want us to see the relationship a little bit more clearly. So if I want to find g prime, so the derivative of this function is basically going to be using the second theorem of calculus, right? So if I want to find g prime, the derivative of f of t dt means that these two operations are going to cancel each other out, because derivatives and integrals are inverses of each other. So if we want to evaluate this, all we need to do is this f of t is not going to get affected. Neither are we taking the integral or the derivative. These two operations are going to just cancel each other out. We just have to plug the upper bound into f of t. So upper bound, and for t we get f of x. So simply g prime is equal to f of x. And that means g double prime will be f prime of x. So we're going to keep on going back to these relationships as we get further into the problem. Okay, so part A, find g of 1. So if I want to find g of 1, I can plug 1 into my formula. So the definite integral from 1 to 1 of f of t dt. No movement has been made between my upper and lower bounds. So if my upper and lower bounds are the same value, there's no area that's to be found. So we know the definite integral is simply going to be 0. To find g of 3 is simply definite integral from 1 to 3 of f of t. Okay, now this is my f of t graph. So from 1 to 3, I can simply look at the area that's covered here. So this triangle, 1/2 base times height, will give me 1, but this is below the x-axis, so therefore -1. To find g of -1, g of -1 would mean that we go from 1 to -1. Okay? And if we have that set up, because that's what the formula gives us, it's easier to think in terms of the lower bound having the smaller value. So even though this is what we plugged in, I'm going to go ahead and change the upper and lower bounds so we can read the graph from left to right. And once we change the upper and lower bounds, to get this lower bound to be the smaller value, we need to pull a negative out. So the definite integral from -1 to 1 will just be the area of half of the semicircle. Okay, now semicircle area is 1/2 pi r squared, and my radius of the semicircle is 2. So pi over 2 times 2 squared will give us 2 pi. So the semicircle is 2 pi, but if I split this in half, this is pi and this is also pi. So the definite integral from -1 to 1 is simply just pi. Okay, but because we pulled the negative out in front, we have negative pi as the value for g of -1. Okay, for part D, find all the values of x on the open interval from -3 to 4 at which g has a relative maximum. So g is going to have a relative maximum where g prime is equal to 0. And since our g prime graph is our f of x graph, we can simply look at this as our g prime graph as well. And we can make a sign line, endpoints being -3 and +4, critical points being +1 and at 3. These are where our x-intercepts are. And if this is the derivative graph, and anything above represents positive slope, anything below represents negative slope. So if we make a sine line, we're going to have critical points at 1 and 3. The graph is increasing above the x-axis, below the x-axis, and above the x-axis. And looking at these arrows, we can tell that our relative max must occur, at x equals 1, because g prime changes from positive to negative. Okay, part E, write the equation for the line tangent to the graph at x equals -1. So if we want to find the tangent line equation, we need the point and we need the slope as well. So g of -1 we found from part C is equal to -pi. So we have our ordered pair, -1, -pi. That's our point. And if I want to find the slope, I need to find the slope at g prime of -1. Now, g prime of -1 is equal to f of -1 because we see that's the relationship between g prime, g of x, and f of x. So f of -1 is simply equal to 2 because I'm just reading the ordered pair from my graph. So f of -1 will be a y value of 2. And remember, all these y values represent the slope of g of x now. So we have our ordered pair, -1, -pi. We have our slope, which is 2. And we just plug into point slope. Y plus pi is equal to 2 times x plus 1. Okay, part F. Find the x-coordinate of each point of inflection. So if we want to find the point of inflection, we have to be able to set g double prime is equal to 0. And if we set g double prime equal to 0, then that's the same thing as setting f prime equal to 0. And if I want to find, and since this is the derivative graph of g of x, then we know the max and mins, or the hills and the valleys, are going to represent the POIs for our g of x graph. So we know our critical point is at -1 and at +2. And we can just make our sine line. Positive slope represents concave up, negative slope represents concave down, and then positive slope, concave up. Therefore, point of inflection is at -1 and 2, since g double prime changes signs at those values. Okay. Part G, find the x-coordinate of each. Part G, find the range of g. So in other words, we want to find the lowest y value and the highest y value for our function. And if we want to find the lowest and the highest values, this means that we're trying to find the absolute max and absolute min. And if we want to find absolute max and absolute min, we have to refer back to extreme value theorem. So we have to test our endpoints as well as our critical points. So our critical points from our sine line from part D is at 1 and 3. So, and our endpoints is at -3 and 4. So we basically just have to find the y values at each of these points, at each of these x values. And whatever the lowest value is will be the lowest y value for our range, and the highest y value will be the highest y value for our range. Okay, so part G, we're going to find g of 1. G of 1 is 0. That's given from part A. G of 3 is equal to -1. We found that from part B. And then g of -3, that's our endpoint. So g of -3, we simply plug into our formula given by what's given to us. So from 1 to -3 means that we're going to have to switch things around. So if I flip the bounds from -3 to 1, that'll give me, I should get a -2 pi here. Okay, g of -3, because I switched the bounds, so I need to pull a negative outside. So initially, this is giving us 2 pi, but we have to change this to a -2 pi. And g of 4 is going to be the definite integral from 1 to 4. So the definite integral from 1 to 4, we can simply look at our graph here. So -1 plus 1/2 will give us -1/2. So we see that our lowest y value will be -2 pi, and our highest y value is going to be 0. So our range should be from -2 pi to our highest y value, which is positive 0, just 0. Okay. All right, let's look at number 6. So number 6 says, consider the differential equation given to us. Let y equals f of x be the particular solution to the differential equation that passes through 1, 0. So for part A, write an equation for the tangent line to the graph. So if we want to find the tangent line equation, first we need the order pair and we need the slope. So the order pair is given to us at 1, 0. Now to find the slope, we're going to simply refer to our differential equation. Remember, differential equation is just another way of saying this is the derivative function. And the derivative function is basically the slope finding formula. And if I plug in the x and y values into my derivative formula, then in return, whatever value we get will be our slope. So plug 1 in for x, plug 0 in for y, and we're going to simplify this down to just be 1 times -3, which is -3. So our tangent line equation into point slope is y minus 0 is equal to -3 times x minus 1, which is simply -3 times x minus 1. Now, once we have our tangent line equation, we can use that to approximate f of 1.2. So all we do is we plug 1.2 into our slope tangent line equation, and 1.2 goes in for x. 1.2 minus 1 is 0.2. 0.2 times -3 will give us -0.6. Part B, find y equals f of x, our particular solution that passes through the point 1, 0. So this is where we have to separate the variables and take the integral, solve for y, and then once we get the plus c, we can use 1, 0 to find our c value. And once we have our c value, then we can write our particular solution. So first step, we're going to separate the variables. So we're going to get divide both sides by e to the y, move the dx to the other side. So we have the y's on the left and everything else on the right. Okay, we take the integral of both sides. Now the integral of e to the y in the denominator, we have to move this up to the top in order to apply the rule for e to the u, which is e to the u plus c. And our u value is -1, negative y. So that's going to produce a -1 when we find the integral. And next, the right side, we go through power rule. So 3x cubed over 3 minus 6x squared over 2 plus c. And once we're at this point, I like to just go ahead and if I can simplify further, I want to do that. And once I simplify this, I'm just going to go ahead and find my c value at this point. Now you can choose to take the natural log of both sides, solve for y, and then solve for c. But I think it's just going to be a little bit easier to solve for c at this point. So it's really up to your preference. Okay, so we've separated the variables. We found the integral. Now I can plug 1 in for x, plug 0 in for y. So e to the 0 is 1, -1 plus 3 is 2. Subtract both sides by -2, and I get 1 minus 2, which is -1. So my c value is -1, and I can now continue to solve for y. Now I want to solve for y. I want to bring the y down from this exponent location. So I'm going to take natural log of both sides. Take natural log of both sides, the -y comes down, natural log of e goes away, and I can divide both sides by -1. And so y is equal to negative natural log of -x cubed plus 3x squared minus 1. So here we have our particular solution to our differential equation.